In the last video, we were talking about column spaces. In this video, we're going to talk about null spaces, the null space of an m by n matrix. By way of a reminder, we said that the column space of a matrix was a collection of all matrices times variable vectors, right? This was a matrix times a vector containing variables. This collection, sort of this entity here, this item, this object, is in Rm, and the vector x came from Rn. So that was how we defined a column space. And we said that this thing that looked like this, Ax, could be written as a matrix, A11, A12, and so on, A1n, all the way down to AM1, AM2, to AMN. It's actually supposed to be 3 dots, not a minus or whatever it turned out looking like. There we go. So that multiplied by the vector x1 to xn. Okay, and this just confirms that these things here are in Rm, they're m-dimensional. This thing here came from Rn. Okay, and then we said that we could write that as the vector A1, the vector A2, and so on, up to the vector A sub n times the vector x1 to xn. That doesn't look like an n, does it? I ran out of room. Let's see. N. There, that's a little better. And by matrix multiplication, this is equivalent to A1 x1. This is a vector times a variable, plus A2 x2, to make sure I put my vector notation over the right thing here, all the way up to AN xn. And what that tells us is that AX, the matrix A times the vector x, is really just is a linear combination of the columns in A, right? This A1 1 through AN1, M1 is represented by this vector A1, and this vector A1 times this variable x1 is a term in this sum. And this sum is just a linear combination of the column vectors, if you will, from A, where the x's, the variable values here, are the weights. Okay, so this is an example of this might be, 3A1 plus 2A2 minus 4A3, and so on. Where A1, A2, and A3 are vectors. They're the columns of this matrix, but written in this form, they're vectors. And so this is just a linear combination of these columns. And that's really what we're saying up here. The column space of A is the collection of all possible linear combinations of A with the vector x. Okay, so now we're ready to talk about this thing called the null space. And the null space, which we denote null of A, or null A, is a collection of vectors x. So now we're talking about things that look like this. The null space is a collection of vectors x coming from Rn, right? These are n-dimensional vectors that make the following statement true, right? That collection of all vectors such that, or so that, Ax equals 0. Now, notice that this is the 0 vector, not the number 0. So what we're looking at here is all the possible vectors of n dimension that when you multiply a matrix A by one of those vectors, the result is the 0 vector. Here's an obvious example. Let's take A equals, just going to go 1, 2, 3, 4. Nice square matrix there. and I'll let x equal the 0 vector in R2, 0, 0. Then AX is equal to 1, 2, 3, 4 times 0, 0. And if I do this row by this column and then this row by this column, I get 1 times 0 plus 2 times 0 and 3 times 0 plus 4 times 0. And I get the 0 vector. So here is a vector x. It's the 0 vector itself, right? Such that when I apply it to the matrix A, when I multiply the matrix A by this vector, the result is the 0 matrix. And that's going to be true for any matrix. The 0 vector here in this position for x, if x is the 0 vector, then this statement is going to be true. And so we can say that the 0 vector is always in the null space of A. Let me use a lowercase n there. Because the 0 vector will always make this statement true. Any matrix A times the appropriate dimension 0 vector, x, is going to produce the 0 vector. So 0 is always in the null space of A. The sizes need to be appropriate. The dimensions of the matrix and the vector still need to be appropriate. But given that, the 0 vector is always in the null space. Okay, so let's see how this might look in application. Let's say that we wanted to find the null space of the vector A equals this. And we want to find all of the vectors x for which A times x, and this x is going to need to have 4 components, right? Let's rewrite this, give myself a little more room. We want to find this vector x so that the result is the 0 vector. Well, this is equivalent to saying, if I took this back into sort of system of equations form, I would have 1x1 plus 0x2 minus 2x3 plus 1x4, plus 1x4 equals 0. And I would do the same thing for the other 2 rows here. There you go. And if I wanted to find a solution to this system of equations, I would write probably a matrix from it. Assuming that I did not have this and that all I had was this, I would write x1, no I would not. I would write 1, 0, negative 2, 1. I would write the coefficient matrix, negative 5, 0, and 1, 2, 0, negative 5. That should look familiar because that's exactly what I have up here. But then I would augment this with the constant matrix, right? The constant vector from here. And then I would row reduce this augmented matrix until I had something I could read off as a solution. So I'm going to do that off screen on my calculator. I'll be right back. Okay, here is my reduced echelon form of the matrix above here. And as you can see here, I've got a pivot here and a pivot here, but then I don't have any more pivots. I have a 0 row down here. And what that means is that I will have an infinite number of solutions, and all I need to do now is figure out how to write them. So if I go back, if I take this form and go back up here and write this as a system, I would have x1 minus 2x3 plus x4 equals 0, and x2 plus x3 minus 3x4 equals 0. And I have in both of these, I have, let's see, where's my pointer? I have an x3 and an x4 in both of them. So I'm going to solve this one for x1, this equation for x1, and this equation for x2. Just do that next. That was going to go here. So we get x1 is equal to 2x3 minus x4. And x2 is equal to negative x3 plus 3x4. So I have here two variables, which each depends on two other variables. So I can now write my solution matrix, which would be x1, x2, x3, x4, as x1, which I determined was 2x3 minus x4, x2, which I determined was negative x3 plus 3x4, x3, which is x3, and x4, which is x4. And in a perfect world, this would be a little bit longer too. There we go. So the solution to this augmented matrix is the solution to this augmented matrix, which is the solution to this system. And that's also then the solution to this matrix equation here. This is AX equals B, where B is the zero vector. That's the result that I want. And what I've just found are the values that x1 through x4 have to be. And that's not a single solution. It's not one solution. It's an infinite number of solutions. But I can pick anything I want for x3 and x4. Any combination of those two numbers, those two values, and plug them into here to find out the x1 and the x2 that will go with them. There's still an infinite number of possibilities because there's an infinite number of numbers to choose from for these two. Once I've chosen them, I can plug them in here to find the values that go with them. So the null space of this matrix A is all vectors that are made up of any two numbers here and these two numbers in a particular relationship with each other based on these two numbers here. The other thing we should note here is about how else we could write this matrix here. It looks like I'm kind of out of space. That's not much of a surprise, is it? Let me erase my arrow. And I'll try just to go up. I want to make this observation. I could write this as 2, negative 1, 1, 0 times x3 plus negative 1, 3, 0, 1 times x4. And what that tells me is that these two vectors, this is kind of old content now, but it's still important. These two vectors form a basis. Okay, but what do they form a basis of? Well, remember that a basis is a minimal spanning set, and a spanning set is a collection of vectors that span a space. And if you think about it, the fact that there are two vectors here, these two vectors form a basis. They form a basis for R2. And what that means is that the entity that we're looking at here, AX, right, this thing right here, is a subspace of R4. Specifically, the kind of thing that this is a two-dimensional subspace of R4. It would be easier to imagine this if we were playing around in R3 instead of R4. Right, this vector is an R4, but if it was an R3, if it only had three components and there were three components here and only three entities in the three values in each row here, then I'd be able to say that these two vectors form a basis in R2, kind of within R3. So the subspace that I'm spanning here is a plane in R3. So if you can picture all of your, picture all of R3, and we want to span this space in R3, what we're spanning is R2 in our, kind of embedded in R3. So we have some kind of a plane in R3. So what we've really found here is a basis for the null space of A. I'm not going to worry this quarter about the rest of this subsection under the null space. After you finish 6.4.2, that challenge activity, you can stop reading there and pick up again where it starts with row space and the left null space. You don't need to worry about reading the theorem 6.4.6 or understanding that. You don't need to worry about determining whether a solution to a system of linear equations is unique. And you don't need to do participation activity 6.4.5. Do, though, continue reading with row space and the left null space.